It's a pleasure to introduce Christoph Minz, visiting us from University of Leipzig until the end of next week. Christoph received his PhD from University of York, and his thesis work was on aspects of classical and quantum fields on puzzle sets from an algebraic perspective. And more recently, he's also been working on modular theory, which we'll talk about in next week's journal club. But today he will tell us about scalar fields on puzzle sets.
Thank you very much for the kind introduction. Everyone can hear me, so if you have any problems in understanding or any questions to the talk, you can just interrupt me and ask any questions. So as Jasman said, I will be talking about essentially about my results from my PhD work, so which is now about 3 years ago, which will be mostly focusing on causal sets, or rather the idea of causal sets, and discussing classical and quantum fields on that. In fact, even though I've written entirely from classical to quantum fields, I will also go in the other direction, actually, starting from quantum fields, turning to classical fields in order to define states. But I will make this a bit clearer in a moment. So, as motivation, why to do causal set theory? Maybe some of you might already know about it. It's a framework to do quantum gravity, and I'm saying here in the way that I'm using it, it's not yet really a theory of quantum gravity because there's no quantity in this theory per se. But I'm only using this framework for sets, so it's essentially like a precursor of quantization theory for gravity, and it's a very minimalistic approach. So it's essentially reducing the structures of space-time to only the causal structure and some volume information. So these are the only two essential inputs that we retain from our theory of space-times. And in fact, it was shown, as you can read also a bit more detail in this review article by Suya, that these two informations are enough on the space-time to actually recover the entire structure of the space. But for causal sets, of course, we want to go one step further. We also want to make this thing discrete. So we actually reduce the number of points to just a locally finite set of points. And I make this a bit more clear in the next slides, where I show some explicit constructions of causal sets for space-time. And then, of course, if you now want to go back, if you now say, well, okay, let's say our space, we assume that we have a space of causal sets, and they meant to resemble some space-time manifold, then you might want to recover the entire manifold in this discrete structure. But this is so far only a conjecture, so this is not really clarified and fully solved yet. There are some attempts in trying to solve that, but it's not fully solved. So this is one idea or one purpose you can assign to causal sets. But there's actually a second one. This is a bit closer to what I've been doing in my PhD work.
So eventually, sorry to interrupt you. What is the open question with regard to space-time manifolds being approximations to causal sets? What is the fact that you're claiming is not settled?
Well, the point is that if you have just a discrete structure like these causal sets, then of course you don't have any. This is not a differential manifold. It doesn't have any manifold. So actually, if you want to do physics on a space-time, then usually you rely on forming derivatives, heavy vector fields, and things like that, which is all a bit different on a causal set because it's just discrete set of points. So you would need to say what it means if you have a collection of causal sets, what it means for a space-time to approximate it. What is the exact notion of it? So this is not, I suppose this is also a mathematical question, but this is actually possible that you could find a unique space-time in some sense to a collection of causal sets. Because a priori it might be that
you have some way the way the statement is phrased, I would have interpreted to mean that there exists a density of space of causal events, which when I increase that density to a continuum value, then it is
Exactly.
it covers a given space-time, which
Yes.
is approximating.
But exactly with
Is there a flaw in that theorem? Or not, it's not a theorem.
well, I mean, it's just a conjecture. So it's just, or rather, it's an idea of what you might want to do. You might want to start with a discrete structure, but exactly what you have said. You're thinking about getting something denser and denser. So we're actually taking a certain limit, and this would have to be made precise what this actually means to having something denser and denser. Because in the actual picture of causal set theory, you might think about a collection of causal sets that are all for essentially for space-time up to some fundamental length scale. So maybe you go only discrete up to Planckian volume or something like this, and beyond that you don't have any other structure. And then actually you don't have this notion of getting denser and denser and denser, but you only have this one fixed collection of one density. And then getting a manifold that corresponds to that might be not unique in its sense. You might find many different manifolds that actually can approximate this.
Okay, so this is distinct from the Euclidean setting where you can imagine a simulation complex that with a fixed number of edges, vertices, etc. That when you make that level of theorem is not doesn't exist.
Yeah, so this is not at least worked out yet. So it might be possible. This might be one approach in a sense to what you touched as essentially connecting the idea of causal set theory maybe to causal dynamical triangulations or other programs of gravity that actually go into this direction. You essentially builds visual complexes out of this maybe. But this is a sort of topic that I'm not going to talk about much here because this is still not really worked out. But what I actually wanted to use more about, or want to talk more about is causal sets, this just discrete model. So if you now put in classical quantum fields on a causal set, then you get finite dimensional models for your quantum theory or for your classical theory. And those models are usually much easier to deal with than the infinite dimensional models that you usually have in quantum field theory.
Can I ask a question, please? May I ask a question? What is the you have not introduced a topology. So what is the meaning of locally finite limits and so on? Can you hear me?
Yes.
Yeah, but I didn't quite get your question. Sorry.
One more question. I have not seen any topology on the causal set. So what is the meaning of a locally finite? And what is the meaning of a limit?
Okay. So exactly these are the open questions that you would have to solve in order to say that you have something like an approximation, that you have a space limit that approximates all that. So these are still exactly like you say, these are open questions. So you have to find some structures to know or to exploit there to actually make this correspondence.
In the end, I suspect that the answer is that it is not unique, because we know that four-dimensional spacetimes have different differentiable structures, and the differentiable structure is not going to be captured there.
Yes.
Because it's a sweet causal structure. Yes. So there must be at least that family of different ones.
That is likely. That's not unique exactly. But okay, let's stick with this example of causal sets for discrete or finite dimensional models for classical quantum theory. And if you want to do this and actually draw some conclusions also for quantum field theory in more general infinite dimensional settings, then you also would have to find a limit procedure for that, which is also not established yet. So if it's even possible, but at least we can deal with classical and quantum fields in that sense for causal sets. This is what I want to come to at this talk. But my PhD, we have also looked a bit more about discretization methods. So in the first point, I want to talk about again about causal sets in classical fields, and in particular about some discretization methods that can be used to discretize the field equations. And in the second part, I will talk about the quantum algebras and what their relation is to the classical theory. And then I will do a very specific quantization technique, namely the geometric quantization and the dequantization, to define a state for algebras. The turn out in the end that actually the state what you get from this approach is in fact the Sorkin-Johnston state. So this is the state which is fairly known in causal set theory. And then I will come to the summary. So first, just to recap, for those who are not very familiar with this process of generating causal sets for a space-time manifold, so I will start with a space-time manifold M. Here in this example, I will depict, because of just simplicity, just M2, like Kasia, that space-time in 2 dimensions. And you can even mathematically write down the probability space for a process called sprinkling. This is essentially a Poisson process on the space-time manifold, where you have some configuration space Q, which is essentially a space that is locally finite in the sense that whenever you take a compact subset of your manifold and intersect it with one of these elements, you get a finite set. And this is a bit abstract still, so let's do this a bit more explicit for some regions. So let's take a dynamic region is a bit cut off here because I'm just having a small picture. But it's take some compact region U, and we can also formulate this probability process there. So this would mean that whenever we do a sprinkle, we just have a finite number of points in this region. And down there in the last equation, this mu you see is in fact this measure, this probability measure that you might know from Poisson processes. And there are a few other maps there. They are necessary to construct this mathematically precisely because, well, what you don't want to sprinkle 2 points on the same point. So you don't want to have a degenerate point essentially in your sprinkle. And then after you've sprinkled, now you can look at every point of your sprinkle, and you can look at what causal relations there are to all the other points that you have sprinkled. In this case here, for this 1 point, we have 5 other, so 2 points in the future and 3 points in the past. And then from that, if you now repeat this for all points and look at the line points, you can reconstruct the structure. So for this one here, we can then put edges in this graphical representation wherever there is no point in between. And this is in fact the way that you get a causal set. So for this sprinkle here, you would get this abstract causal set. So this is causal set you get after getting that you actually had a manifold in the first place. And you only remember that you have a set of points, which in general are actually not labeled even, but they are only distinct by their causal structure or by their partial order to all the other points. And this is actually the mathematical way to draw this was quite commonly done with these Hawkins diagrams where you just draw the edges, as I said, between 2 elements if there's no element in between. Or the other causal relations can be inferred from transitivity of the partial order. Now, here's again the definition of a causal set. As I said, it's a partial order just with this local finiteness property. So whenever you take any interval in the set, you have to have this to be finite. And this, in fact, corresponds to the notion of local compactness of space-time manifolds that we usually consider in physics. For the following slides, I will use this example here on the slide as a causal set. So this is one example of a causal set that needs at least 4 dimensions of the Kasia space to be embedded. It's essentially the simplest causal set you can think of. This is a 3 simplex represented in the causal set, and we will use this as an example. So now we want to do classical field theory. So what does this mean? We actually only look at the collection of elements that we have in our Causal set, and this is just the set of points. And for every point, we define a field. We just assign a real number to it to every point. And in this particular example here, where I have just a finite Causal set, in fact, we can represent this with Rn. So our configuration space of fields on this Causal set is just isomorphic to Rn, and we can actually use Rn so that everything following from that will become matrices. And then the algebra on these fields are, and essentially in this finite case, are just matrices, or represented by matrices. More general, they are functionals on this configuration space to complex numbers. And you can even use this very abstract general definition for scalar fields, curved spacetime or general manifold. And with this, then you can find a Causal bracket also for this space of classical observables. This is yet off-shell, so there's so far is no equations imposed. And there's a paper there where you can find this a bit more explicitly done for Causal sets. And then the next thing, as I said, we now want to actually impose some field equations. So what I've introduced is, of course, the scalar field. So let's do scalar field theory on that, and this is usually done by the Klein-Gordon equation, which is looking like that. So we have a differential operator which acts on the field, and we now want to discretize this notion of the operator. And quite commonly, this is done in Causal set theory by expanding this out at every point x of the Causal set, expanding this out in a series where you say that you want only this point x to be influenced by its past. So you have you layer the past in this picture. You have the first layer, which are all elements that are directly linked to it, and then you have other layers. Here, this particular example, you only have a third layer and a seventh layer down there. And these points then go into this explicit formula, and then you need to find now some coefficients C that I have in there that actually correspond to your spacetime that you want to represent. This is somewhat also a disadvantage because in this discrete approach of the field equations, you will need to know what your spacetime actually is, because all the information about the spacetime is hidden in these coefficients, which have to be fixed by comparing this discrete approach to actually a spacetime manifold. So you do some sprinkling, and there's quite a lot to get some statistics, and then from these statistics you can derive these coefficients. But of course, this is somewhat a downside, because actually we want to think about Causal sets as maybe as a more fundamental thing, and then we wouldn't really know what a spacetime is. So these coefficients are not known. And there was this paper which I mentioned earlier, which actually suggested to use a different structure, a so-called preferred path structure. And they have started with some lattices on a two-dimensional Minkowski space, and derived also the D'Alembert operator, so the essential part for the Klein-Gordon field equations, and use this to discretize the fields. And in my thesis, then I generalized this to lattices in higher dimensions. But what is still an outstanding question that we haven't answered yet, because this needs some mathematical studies, is whether this alternative approach is actually a good approach also for discretization of a Causal set, in the sense that it is actually maybe even better than the previous one, so that the coefficients that you would get don't depend on the spacetime dimension. So for lattices, I've actually shown that the discretization that you get out of this is almost spacetime dimension independent. So the coefficients were almost the same for dimensions. And this is because, in general, any element, if it's actually part of a higher dimensional Causal set, then it usually has more neighbors in the path, and so the layers are bigger and bigger the higher the dimensions. So in some sense, the Causal structure already knows a lot about what a dimension might be. But now, as I said, we want to actually go a bit more towards quantum theory. So what's important there is now we want to find solutions, general solutions first to our field theory. And for that, we usually use the retarded and the advanced Green's operators. And for quantum set in particular, we can define the retarded operator as just the inverse of this field operator. You can actually show that the operator in this matrix form is actually invertible, and you can define a retarded operator like that. And this is because the P we have also defined as a retarded operator only looking into the past. So this is the retarded Green's operator, and then with this we can define our Pauli-Jordan operator as the essential input.
So these are left inverses probably and right inverses.
These are because we are just in the screen settings. This is actually the same. The left and right inverse is the same because they are just matrices.
Okay.
The left and right inverses in this algebra is the same. Okay, so and you can do a similar approach. Of course, you wouldn't use the inverse of P, but you can also formulate a retarded advanced operator for a space-time manifold. And then for space-time manifolds, we actually know that the solution space, as we usually want to take as the kernel of this operator P, is actually equivalent to the image of the Pauli-Jordan. But this actually only holds for space terms. So because we have constructed our retarded Green's operator for quotient sets with the inverse of P, that doesn't actually hold anymore for quotient sets. So the image of E is not the same as the kernel of P. But we can instead just use the idea of the space-time and set our solution space to the image of E. And that then actually works. Which is maybe just some side detail, but it's, yeah.
So yeah. Just the image of.
Well, because everything, so on the space-time manifold, of course, everything is in the image of the Pauli-Jordan operator.
So
if you now apply
P again,
I'm
just trying to think through, what does it mean that the image of E, which is the difference of the two, is not the kernel of P is now 0.
Yes, because we have said
that
this is an invertible matrix, so it has to have the trivial kernel.
But it wasn't an invertible matrix to begin with. You're only inverting it and it's non-zero subspace.
No, for quantum sets, it's an invertible matrix. It's just not an invertible operator if you would have it on a space-time manifold. So in the more general setting, it's not an invertible thing. And that's why you can actually show.
So in what sense is it not an invertible? It's invertible. It is 0 on the past, so it's not invertible. So you're saying you're just inverting it on.
No, I mean not invertible. I mean on the space-time work, P, maybe to recap, is the Laplacian plus squared on a space-time. So basically, it's a differential operator.
Okay,
the just doesn't quite make sense.
So the m squared is what's making it not invertible. It's making it invertible.
The what? Sorry.
It's because you've added an m squared that it's invertible. Is that what you're saying?
No, you can actually also forget about the m. Because it's a differential operator.
If you go back to the previous slide,
yes,
you had P defined there, and it is 0.
Well, this
the points below the one.
Yeah. So again, this definition of P, or this discretization, is only for a quotient set. And this, I mean, this is the idea for the space-time. And for quotient sets, you have some discretization scheme.
Yes.
And so for quotient set, let's say maybe I put a discrete here. you have this discrete version. This is actually this option.
So, and it's 0 on any of the points that do not enter P1 and P2, etc. There are points in the past here.
It's easier.
Sorry?
It's first coefficient on the right.
It's not 0. It's
C0 is on
you have this expression for every point of the causal set.
So C0 is non-zero for every point in the causal set.
Yeah.
Okay.
Yeah.
Past and future.
Yeah.
Yes. Okay. Yeah. You only look at so this P only gets information from the past for every point.
But and the future of that. So this is,
And so now you can go do this for every point. So you can also go to this future point and this is influenced by
and P is defined for all of those ones.
Yes. So this is still depending on X. So sorry, I should actually change this set there to X. So this is all X's.
But if it's a retarded operator, so we just look at the past.
Yeah, but and what happens in the future then? It must be 0.
No. For every point in the causal set, it's always looking into its past. So for every point of the causal set, no matter how far you go into the future, you always have a past.
So I think of it as a matrix.
That's what I'm thinking of that. And I'm
so-
thinking of it as if I was to form
Yeah. So it's
one index is any point in the causal set. The other index is everything to the past of that other one.
So what is actually as a matrix? It's a triangular matrix. So you have quite a lot of 0 entries. That is right, but it's only one triangle of this.
Oh, so that's my problem.
Yes.
It's triangle. Yeah,
And this matrix is
0. They're on one of the triangles.
Yes.
Okay.
And exactly because of this, because it is a triangle, I mean, so you can actually fairly easily show that it isn't invertible, and you can make sense of this expression of the form.
No, that's just I'm okay. There had to be these zeros. I just
Yeah.
I had them in the wrong place in my head. Okay.
Yeah, that's why there's this difference for specific situations. Okay. This is also always an fact that had been noticed by Sorkin's earliest work. I think there's a problem with this P essentially and image. But okay, we actually want to come to the quantum theory. So first we define our Poisson structure or Poisson bracket, and that can be done by a method of science, where essentially this Poisson bracket is completely just determined by this Polyjoule operator. This is now still off shell. And then okay? So now we have now that we have that, we want to go to a quantum theory. And what does it actually mean for a quantum theory, or what do we want from the quantum theory? Well, for the quantum theory, we want that in some sense we introduce a new parameter, the h bar parameter, and we know that we want to somehow recover our classical theory if we send this h bar to 0. So we have to make this a bit more precise what it means that h bar goes to 0. But for now we know that let's say we have some quantum algebra with some multiplication. So this is just this math frac A algebra there, and we have a classical corresponding theory. And this classical theory corresponds in the sense that, well, if we take any product in the essentially the quantum world and would now send the h bar to 0, then we wouldn't want to recover the classical pointwise product of our observables in the classical theory. And similar, if we do this for the commutator in the quantum theory, we want to recover the Poisson product. These are essentially the two most important conditions that we want to put on. And of course, in general, you can also have that our observables by itself depend on this h bar parameter, and we want this to match our classical world. And quantization is usually seen as going the other way around. So we know that we want to have these limits, and now in quantization, you usually try to find a map that assigns to every classical observable some quantum observable, such that this actually holds for the algebras. Of course, you would have to make sense that taking this limit, so you actually need to construct algebras for all values of h bar, and you might want this to be continuous. I'm not going to too much into the mathematical details about it. What I would rather want to find out, like what quantization maps could we find. In general, you might think, well, okay, if you only have these two conditions, you only have this limit for the product and for the commutator. What about just saying that essentially you use the second equation and that quite literally and just say that your quantization map should fulfill this. But it was actually shown by quite some time ago already that this can't be realized by quantization. So in fact, what you have to have higher orders of h bar, and they don't really matter because in the classical limits they all disappear. And so in general, what is an approach is quite often taken is a formal deformation quantization, in the sense that we now just have these two conditions that we have seen on the last slide in the first orders of this expansion, but we allow for higher order terms in h bar. So we have in our zero coefficient of this expansion, we have our product, and in the first order coefficient, we have the commutator or the Causal product. But note again that we have now a lot of other coefficients that are not really fixed. So in this sense, the star product is not unique. So you can find different star products that realize similar quantum algebras. And in particular, what is maybe a bit more interesting for the physical setting, or going towards some algebra that would also solve the field equations in class limit, is that we can consider these big products. And they are a bit more abstractly written here with some real part h, capital H, and then in this for the Z setting, which I want to focus on most, is that you have these given as matrices. So this W is in fact actually something like a 2-point function, and that is constructed from this E from the Pauli-Jordan operator we have seen earlier, and some other real part H. And on this real part H, we just put a few conditions so that the W is so this is the real part of this W, and we want the W to be positive, definite. And we want that the kernel of this operator actually contained in the kernel of. And if you set out these conditions, and if you do the same procedure for space-time manifolds, it goes through the calculations, you actually get out from these constraints the standard equal time commutation relations that we know from PLC real lectures.
Is that a typo that you wanted W to be greater than 0, since you wanted positive definite, presumably, or are you allowing 0? So it's semi-definite.
Yes, it's true. It's a typo. Yeah.
You want it to be positive.
Positive.
You don't want to allow 0.
No, I think you can actually allow 0.
So you want it semi-definite.
Yeah, I would have to check this. It's a good question, because I mean, I will come to some very explicit construction into the Sorkin-Johnston axioms. And in those, you only require positivity. It is actually corresponding to this, and then this would also allow for 0. So this goes back to some earlier works from Sorkin-Johnston, and they sort of in a similar line about the operator E, as the Pauli-Jordan operator, as an input, and to find a 2-point function that actually fulfills these conditions. So you would have this first condition, which I call the commutator condition, which essentially corresponds to our real part in these big products. Then the positivity is fully valid, corresponding to this semi-positive definite. And then the purity is a bit of a stronger constraint. In fact, you can find a unique solution to these conditions, which is known as the Sorkin-Johnston two-point function. And as you can see from this, actually, this is so far stronger as the kernel is the same. So for WE. And all of these constructions you can also do for space-time manifolds, but the states you would get from this construction there are not known to be not hard. So you would use this condition, but you can reinstate or fix that by actually modifying an inner product. Now you might ask, what is an inner product? Actually, in this purity condition, because now you're taking the product of two matrices. But actually, they're not really matrices, they're actually two forms. So you have to make sense of this product by essentially lifting or erasing one index. So there's hidden there some matrix in there, which is usually for the set setting that I had before. It's usually taken to be the standard inner product, the standard pairing of the elements that you have. But in fact, you can also use any other inner product or any other metric on that, and then you would get in general different states. And
so just to clarify, you're saying that this Sorkin-Johnston form is not Hadamard.
yes,
How different from Hadamard is it? What is where is the Hadamard?
it's essentially failing to be Hadamard on the boundaries of the space. So they have looked at static slabs.
Locally in the interior, it is Hadamard. You get the right singularity structure.
I think so. I would have to check, yeah. So it's definitely failing to be Hadamard along the boundary. So if you have like some space-time slab, and then you go close to these boundaries, these dynamic random boundaries that you have introduced, there it definitely fails to be Hadamard. But it's not that bad. It's fairly. Yes, and you can also do so. All of these constructions, of course, are only for scalar. You can also do a similar construction, which are just becoming more complicated for fermions, which has been shown. Okay, so another quantization method is also quite often taken, and which I want to introduce here because it helps us to understand a particular type of states, namely the state that the Sorkin-Johnston two-point function corresponds to, is the Weyl quantization. And the Weyl quantization is usually, or the Weyl algebra is constructed in such a way that you start from your phase space, so essentially the solution space that I mentioned earlier, which is a real vector space for setting of total sets. And you have a Poisson bracket on that to the classical observables, the Poisson relation, and then you look at the linear observables in that space, which are essentially just a dual of this vector space, and they have to fulfill these conditions with this abstract map W H bar. And in fact, you can actually show that this H bar fulfills the conditions that we had earlier for a quantization map. So this is a quantization procedure that you can do. And now, what is the state in the algebraic setting? Well, it's just a functional on your algebra. So if you have your quantum algebra A H bar there, then this is a functional to the complex numbers, and it has to be positive and normalized, which you usually want to have. And the quasi-free state is then a state that something we would call Gaussian, which if you when you evaluate it on one of these Weyl generators, you actually get this Gaussian profile, and that's why it's so-called Gaussian state. And in fact, if you do this for the Sorkin-Johnston construction for the two-point function, you see that this corresponds to a quasi-free state. So all the endpoint functions are actually completely defined by the two-point function from Sorkin-Johnston. And you can find this covariance of the state expressed by the modulus of this operator E, what we had earlier. But this is now on the solution space, where this actually makes sense to be inverted. So far I've talked about this formal deformation quantization as one method. You can also do this strict deformation quantization, which then gives us the entire field for all values of h bar, where you can make sense of taking this limit, which I'm not going to talk about too much today. Then I've also previously said something about wide quantization. Now I want to take the approach of geometric quantization, which is essentially starting from a similar input as we had before, which was a real vector space for the setting of Causal sets. Then you construct a line bundle on that, which has to fulfill. Oh no, sorry. So first, we want to take this geometric quantization, and then we want to find a dual operation to quantization. And the dual operation means that we go back from our quantum algebra to the classical algebra, and we can find. And if you can find such a map, we can actually also use it to construct a state in the sense what I have said on the previous slide. So to essentially build a functional on our quantum algebra. So our input for the geometric quantization is very similar to what we had before. We have a two n-dimensional vector space S. We have an inner product on that space, which is just the pairing of vectors. And then we have a symplectic form that essentially comes from our Poisson bracket that we can invert whenever we are on the solution space. So for this, at least for this very specific setting of a Causal set on a finite dimension or finite Causal set. And the geometric quantization, as I said, starts with this quantization bundle, so it's essentially just a bundle that is given by some connection nabla, and this is given in such a way that the curvature of this bundle is determined by the symplectic form omega in your space. And then there's also the h bar in there. And
you say that he is closely related to Sorkin-Johnston.
Yeah, because the polytope operator, as we constructed before, was an operator on the on the off-shell algebra for the off-shell algebra. So we had the Poisson bracket on the off-shell algebra, but we need to quotient by the kernel of E first, and then we get a corresponding operator on this. Essentially, it's just the polytope operator on the solution space. Where we can, because we take this inverse here.
That's what you mean by it.
Yeah,
It's a Poisson bracket on a larger space, and it's still it's the quotient is there.
Yes, exactly. So we take a quotient. So this is what is meant by being related to this. And the second step in the construction is that we now need to find a physical Hilbert space. So this is quite often useful to have the Hilbert space, and we actually identify this by taking this connection of the bundle and forming this Bochner Laplacian, and then looking at the spectrum of this Bochner Laplacian. And make this a bit more explicit in so this is just the rough idea of doing geometric quantization. If you do this for this finite dimensional vector space, then it has been actually shown that the spectrum of this operator takes this form where we have some strictly positive numbers theta I there, and these are essentially coming from the entries of our E operator that we had before. And for a two-dimensional space, so where this capital N is 1, would have actually this form of a single harmonic oscillator, and we get the spectrum where we have a ground state, and we actually want to identify our Hilbert space with ground state. But if you have a higher dimensional setting, then you get more and more levels here, but you always have the spectral gap between the slowest value and all the other levels. And in that way, you can identify your Hilbert space from the sections that belong to the lowest part of this spectrum. And you can even do this in some settings where you have just a symplectic manifold, so more general settings, because this spectral gap is quite commonly also there in some general cases. And then you can just take all the sections that belong to the lowest part for your data space. And more explicitly,
You skipped over the requirements for the line bundle. And usually people talk about ample line bundles and various technical things like that. These issues don't arise for you.
well, because the line bundle has to fulfill this curvature condition. You fix your curvature of the line bundle with a symplectic form. And so to make it actually a bit more explicit for the vector space, we can use some nice coordinates on our vector space, which are just complex valued coordinates. So just use the set there, so that we essentially now have many of these complex variables as coordinates, and then the lowest part of the spectrum, or the eigen vectors of that, are the holomorphic sections. So these are just sections that eventually have this Gaussian part there, and just some holomorphic function as an amplitude essentially for these. And we can write write a basis for this vector space, for this Hilbert space. And that is also normal in the sense that we commonly know from quantum mechanics we can write something in these n dimensions. We can write this normalized product. And then, in a similar way, with using the spaces, you can also find abstract ladder operators, because you essentially just have an n-dimensional harmonic oscillator. And these are expressed in terms of these the curvature that I had on my line bundle. They go like that. But these are now unbounded operators like the harmonic oscillator as well. And with these sections. Now, because remember, these are just a subset of all the sections of the line bundle, so just for the ground state. We can actually project down to these. So we take any classical observable f, and we can project it. Or in fact, we can't do this mathematically with every one. We actually use just compact operator. We just use Schwartz functions and map them to compact operators in the sense that we project them down with this projector pi, capital pi there, and this gives us a quantization map. This gives us a quantization procedure. This is known as the triplet quantization. And we can actually, even though this is per se just defined on compact operators, we can extend this to bound operators in the Hilbert space. And then the dual operation that I talked about before, that you want to construct, is now going in the other direction. So if you take any compactly supported function f, then you take the trace of the corresponding triplet operator, and you want to find a measure mu such that this relation there happens. And in fact, for the triplet quantization in this particular example, you can do that. And what you get is this Rejzner triplet dequantization map. And that takes you back from the quantum algebra to the classical algebra. And in the picture, is essentially like this. Like we have this blue map up there, which is mapping from this first disk on the left there, which is representing the classical algebra, to your quantum algebra, and then the dual map maps you back to the classical algebra. And the measure for this particular example here is just a volume measure on your vector space, multiplied by some factor that comes to h bar there. So this is just an implicit definition of this dequantization map, but I will come to some more explicit expressions later on.
So what was the dequantization?
Sorry? It's an implicit definition of this. So you take any operator product A times some tempest operator, and then you say that this expression has to hold. So this integral that the dequantization map there has to hold for all objects that fix the product functions. And this implicitly defines the quantization map. So this sign map.
So this
capital sign.
capital sign, yeah. This one is meant to be the dequantization of A. Is that what you mean?
Yes, exactly. So this psi h bar of A h bar is essentially the classical observable that corresponds to this A.
Because you have given us a standard product realization of the trace, and so it should just correspond to dropping the stars in that. Is that right?
Sorry?
You have given us a definition of what the trace of AH, TH effectively in terms of star products earlier. I presume I can still use that. And this expression on the right then is equivalent to dropping the star products. Is that what you mean?
Well, so yeah, I mean, you can relate this also to star products, but so on the left hand side you just have it can be a star product. So it's the product on your quantum algebra. And at this point, it's a bit more abstract at this point. So it doesn't need to be a very specific. So I mean, the algebra has a very specific product.
It just doesn't seem right to me. It's my problem. The equality there just doesn't seem right.
Okay.
It should be an arrow to it. That if it's if you get a dequantization map there, the left-hand side has a realization in lots of examples where you get the thing on the right with lots of star products in there, but the dequantization one involves dropping the star products, and only if it's a quadratic form in there do you get equality. Generically, you don't.
Well, the trace is also not necessarily defined for all operators. So you can only do the
trace is defined for all operators, but if AH involves a product structure, if it's a product of different operators, then the dequantization of the AH is not this. It involves dropping star products in there, and it just won't be equal. One can easily give examples of that. So equality just doesn't look right there.
Yeah, maybe we can talk about this later.
Sure.
Because I'm actually curious about what you mean.
Sorry, what's gamma back there?
Sorry?
What's gamma? On the previous slide.
Sorry?
Don't see any gamma.
TF and J are elementary gamma.
Okay. So I haven't mentioned this. So this is, I mean, this picture that I'm drawing there. It's just a graphical representation of this field of algebras which you would have to construct. So this is actually, in a sense, of strict deformation conversation. So there are these lines which are drawn there are sections in the sense that they have to be continuous on this field. But as I said, I'm not talking too much about this because of time and time reasons. But you can find this in our paper if you're interested. Now to make these expressions actually a bit more explicit, I want to take the I want to make first the y relations or the y operators a bit more explicit. in this particular choice of coordinates that I had used here. So we can write any linear observable phi with these coordinates like this. We just use these components there, and then we can define this more abstract symbol capital phi here with the Dutch operators that we had on the few slides before. And with this abstract symbol, we can actually define like operators that in fact fulfill the Weil relations. And then if we now want to evaluate the quantization map on these Weil generators, for example, then we need powers of these this abstract symbol. And whenever you do this, now you have different ways of ordering the operators. So in fact, when you expand this product out, you can, for example, order all these A minus operators to the left of the A plus operators, which is quite often referred to the antinormal ordering. And in fact, that ordering corresponds to the Toeplitz quantization. If we order it the other way around, then this is compatible with the C quantization corresponding to this Toeplitz quantization. And if you do this now for all powers, you can find actually some explicit relations between the Weil generators, and I've introduced on the previous slide, and quantizations and dequantization of these oscillatory functions, so just e to the power I phi. And in that expression, you see actually that because we know from the Weil relations that the Weil generators have been constructed in a way that they are normalized, so 2 to 1. So if you take the norm on these algebras, they are 1, and that means that the Toeplitz operator, or the Toeplitz quantization is somewhat contracting, because we have this exponential factor there, which is essentially bigger than 1. And so this is in a sense contracting. So this is what I tried to visualize in this picture. And the dequantization goes now in the other direction. So if we dequantize these Weil generators, then we get back our starting function, but this is now modified by this Gaussian terms. And now this comes a bit closer to your question also with these sections here. If we now collect or do this construction for all values of h bar, then we can repeat this, and now we collect this for all values of h bar. Then we can, for the Y section, for example, we can construct a Y section by just collecting all these values, and this would be one of these lines in this picture. And you might note that if we send formally the parameter h bar here to 0 for all of these expressions, then we get each of these expressions back to the e to the I phi, so to the all come back to the same level. And if you now, so far I've only shown you the expression for a single Weil generator. You might want to know also what it would look like for a general Schwartz function on the vector space. And of course, you know what the Fourier transforms look like. So these two expressions, the Fourier and its inverse, we can actually use these to also express any Schwartz function or any Toeplitz operator of a Schwartz function using this, because the e to the I phi expressions in this Fourier expression can be essentially replaced by the Weil generators by using this these factors that we had seen on the previous slide, which I call here a square root of b, which is a bit more involved expression, but it actually has a meaning why it's this square root, which I will come to on in the next slides. And and with this we get some explicit expression for the quantum version of the Fourier transform. So we can write any Toeplitz operator in terms of these Weil generators and with some factors. And now knowing what our while generator is, we can actually evaluate this dequantization method that I constructed on the while generators, and then the result is now a function, a classical observable again, and we can evaluate at 0. If you go through with this, you will actually find that this is equivalent to the Sorkin-Johnston state. And this comes from the, so here I essentially copied again the expression from the dequantization before, where I now set or replace this phi by 0. So, or I evaluate the phi at 0. So this drops the factor e to the I phi, and this just keeps this Gaussian profile there. And for Toplitz's operator, so for general Toplitz's operator, the state would be this composition of the two maps, so of the Toplitz quantization unit varies into this dequantization. And if you do that for a function, then you will actually get to this so-called Rejzner transform. This is now this, why I call this the square root on the previous page, because this is now the square of this factors from before. And in general, we have a convolution of this. But if you do this convolution and then you take the evaluation at 0, then this is actually just the integral over this Gaussian profile of the functions. And I think with this, I'm actually coming to the end. I probably want to summarize again. So what I've done in this geometric construction is we've started from some real vector space S. Is 2n-dimensional. We had given some inner product. So if you would choose, well, if you would have a different inner product, then you would also end up with different states. So this is actually the state that we get out in the end, and it does depend on the inner product you had in the first place. And we also had some symplectic form on the space, because it's a symplectic vector space. And with this, we constructed our a state, which then turned out to be the Sorkin-Johnston. And why we've done all of these abstract things, because we could have done this in a simpler way. The idea is, of course, that maybe we could now generalize this to more complex settings, where maybe other approaches would not work that nicely anymore. In particular, we might want to look at interacting field theory, where you could, if you would do this now for the star products, you could now introduce another deformation parameter. So you would have deformations not only in h bar, but also in some coupling constant lambda. And then this would essentially give you perturbation theories around the unperturbed theory. And but of course, maybe perturbation theory is in essence not very satisfying, because you always have to compute all these terms. And so the idea is, with the geometric quantization, you could maybe get a non-perturbative solution to it, if you can solve this problem of the geometric quantization. Yeah, so this is essentially the main motivation behind it. And with this, I would like to thank you for your attention. And if you have further questions, you can ask them now. Are there any other questions?
So how far have you pushed this for the Sorkin-Johnston? Because most of the last part was geometric quantization.
Yeah, so we have actually not done this geometric quantization for that. So what we are working on at the moment is to try to do interacting field theory with the star product formation, essentially, like having deformation star products, and then go into some order and compute this numerically for some settings. But then, yeah, so the next step would maybe be interesting to check how much is possible for the geometric quantization approach. But of course, it becomes already more complicated, because you don't have a vector space anymore in the interaction picture. Not necessarily, so you just have a manifold. And then this business with the line bundle when it becomes more complicated.
It isn't obvious to me that the deformation quantization you're doing there, if I did it in flat space, would coincide with the usual quantization. Your geometric quantization is introducing some form of stamp products and is it guaranteed to reproduce? If I use the Sorkin-Johnston or some variant of it,
So for
the symplectic form,
so you mean if
I
you
use the deformation quantization that you use there, will I reproduce standard results for a quantum field theory in flat space?
yeah, so I think you can also construct the Sorkin-Johnston state with the deformation quantization approach. So, and essentially also by some, so you construct your state, and then the state is also essentially an evaluation at zero. Sometimes, so it's very similar to this construction. But for space-time manifolds, I'm not sure. I think this has not been done for space-time manifolds.
But it has been done in what sense? You said you think it works.
Well, yeah, for causal sets, as we have shown here, so you can reproduce this sort of set. But so for space-time manifolds, I'm not quite sure.
Just even Minkowski space.
Yeah, for Minkowski space, yeah, of course.
Using this approach, this deformation quantization approach.
I'm not sure. I think this hasn't been done. Yeah. But I would expect that it might also work in a similar way. If you can make sense of all the expressions, I'm not sure, because you would, in general, for space-time, you would of course have infinite dimensional.
You have infinite dimensional also.
So I'm not sure if it might become too complicated.
You could make it into a Lorentzian torus.
Yes.
A cylinder, for instance.
Yes.
Just as
yeah.
You could, where everything is controlled and it's countably infinite rather than.
Yes. So yeah, if you have like essentially a compact manifold as the Cauchy's surface or something like this, then I suppose that could work. Yeah, but I'm not aware of this has been done. I'm not sure. Maybe it has been done. Other questions?
I think you're around for a week, so people can ask you.
Yeah.
In the next
So I will be around the institute.